This lecture is being brought to you in part by the generous gifts of these sponsors.
When I hear these introductions, I wonder, did I do all that? I remember all of that, but not all at the same time. What I'm going to talk to you about are a mix of planetary science and paleoclimatology. I'm a rock guy. When I went back to study rocks at the University of Washington initially, before going to Brown, I was poor as a church mouse, and I needed a job. And a guy was having trouble finding somebody who would be willing to spend 20 hours a week in a walk-in freezer cutting up ice cores, which is what I did for 3 years. Because these were ice cores from Antarctica, from Greenland, from ice caps in the Andes. And what this is a record of past climate. And I'll show you a lot of this. Some of this data I'm showing you I actually took as an undergraduate. And I look back upon that as one of the most amazing jobs I ever stumbled into. I wanted to do planets, but paleoclimatology is actually the study of how planets react to different circumstances. And what I'm going to show you is reality. I'm not a modeler. I have trouble thinking about inventing systems. What I have to rely on is observation and looking at what the rocks tell you, looking at what the data tells you. And there's a difference between having faith in science and observing science. Scientists don't have faith in science. We're always trying to test it to see if it's wrong. What we want to do is we want to observe reality. And I'm going to give you the context of our current climate because we're actually in an unusual place. And part of it is our doing. Part of it is the doing of the Earth's systems. And what I will tell you is not soundbite science. This will actually take 50 minutes. You can't distill a lot of this into a tweet. And I'm sorry, but that's the way it is. And so what you're going to get from me is the context. And so you can go out and see the tweets and realize that, oh, that person is proclaiming to the world how stupid they are. And I get a lot of that. And quite often I bite my tongue and say, oh, very nice, but have you considered, and generally not. So, start with, you hear lots of things about climate. All of this stuff that I'm listing is true. CO2 was a lot higher and a lot lower in the past. The Earth was a lot warmer and a lot colder in the past. Glaciers are melting, sea level is rising, but we're in an ice age. How can we be in an ice age when the glaciers are melting? Sunspots cause warming, greenhouse gases cause warming. This is all true. What I'm not going to talk about is weather. Weather is hard. Weather is huge computational fluid dynamics. I can't do that. I'm not that smart. I'm a rock guy. And the rocks will tell you what the climate was like in the past. And climate is what happens over long periods of time. Climate is easy. Weather is hard. You can't predict weather more than 4 days in advance. But I will predict to you right now that early April next year will be warm and sunny in Florida. Am I brilliant? No. It's just that it happens that way every year. And you can see that in the rocks and strata that are laid down at these times. And you can go way back. So I'm a geologist. If you want to know what a normal climate is, you look at the geologic record. And this is not rocket science. You can actually read this straight out of the rocks and chemistry that were laid down. The problem, of course, is that we all live in human time. You know, the proverbial 70, or hopefully it's longer than that, because I'm past 70 already. Geologic time is written in centuries, millennia, eons, millions of years, billions of years. And we actually know the climate for the last 500 million years pretty well. And so we can answer the question, what is normal? And this is the last 500 million years. We are here. We are in a relatively warm period of one of the coldest periods in the last 500 million years. You happen to be in an equitable period, which is actually unusually cold for most of Earth history. Normal for Earth is way warmer. And we'll talk about that. So 50 million years ago, and that was kind of average for the last 500 million. You had warm adapted vegetation and critters north and south of the Arctic circles. So you can imagine crocodiles and turtles in Hudson's Bay. No continental glaciation, so no glaciers on Antarctica or Greenland. Brownleaf evergreens north of the Arctic Circle. Average temperatures at the poles would be above freezing. You had tropical conditions at 40 degrees north and south latitude. That's the latitude of Ohio and New York. Imagine coral growing off of Long Island. Imagine no hard freezes in temperate latitudes. Like people would want to stay in Ohio rather than moving to Florida. Why? Well, you had CO2 at 1,700 parts per million, and I'll talk about CO2 levels a lot. Right now, the CO2, I checked yesterday, is 428.6 parts per million. Before industrialization, CO2 was about 260 parts per million. And we'll talk more about this, but that'll give you the range. 50 million years ago, it was 1,700 parts per million. And so you were much warmer, but there was this downside. Basically, all the dark bluish-green areas right here are inland seas. Without any continental glaciation, sea level is much higher. So places like Florida were just a dream of somebody. They didn't exist. You had this huge inland sea that stretched all the way across North America, north-south all the way across North America. You can actually see those sediments as you drive out of Denver on Interstate 70. There's a park where you can go and stop and go look at this. I recommend it. It's fascinating. The Middle East was not a problem because it was underwater. So, good points and bad, good things, bad things. And you say, hold it, what's normal sea level? This is what's called a veil plot in geology. It's the result of a huge legal battle between what became ExxonMobil and the federal government, because they were supposed to publish the data that they were getting from drilling on federal land. And if you want to find oil and gas, you need to know what sea level is to huge precision. And they care a whole lot about this. And so this is reality. Our current sea level is actually quite low relative to history, because if you don't have continental glaciation, you have higher sea levels. Now, sea level was lower during glacial maximum times because, of course, you took the top 300 feet of water and you converted it into glaciers and you ground up the northern U.S. We'll get to that. But the point is, this is not normal sea level. I kind of like this sea level. I think we should keep it, but it is not normal. The recent climate And again, we're at 0 here 4 million years ago. So we're here, and we are in one of these a slightly warmer time of some of the most excruciatingly cold times in the last 400 million years. And so the climate has been deteriorating for the last 50 million years. Now, how we know this? We look at oxygen isotope ratios. This is what I did standing in this freezer, was I cut up ice to look at their oxygen isotope ratios. You measure the ratio of stable oxygen 18 to oxygen 16. And if you want to know the details of how this worked, I can go through it in excruciating detail. Because I had, what else to think about when you're standing in a freezer? But the way it works is that bigger numbers are colder, smaller numbers are warmer. So from this point of view, this is warm up here, this is cold down here. And we know this, again, to excruciating detail because things like oil and gas and paleoclimatology care a lot about this. And they've nailed this down. What happened over the last 50 million years is slow deterioration in the climate. And over the last 2.7 million years, this has climaxed to a whole series of glaciations. Over the last million years, the glaciations have greatly increased in intensity. And this is this warm-cold thing again. So warmer up here, colder down there. If you want to know details, I can provide details. I don't even want to know the details, but anyway. And for the last 500,000 years, the pattern has been 100,000-year very cold periods broken by short, on average, 4,000-year interglacials. We're in an interglacial right now. This is our interglacial, and it's extraordinarily long. It's extraordinarily long because we as humans have intervened in the climate. And I will talk about how we do that. What caused the climate to deteriorate originally? Well, this is one thing that you can blame China on, and India. What happened was that continents drift. They move around, and the continent that used to be India, before it got stuck onto Asia, slammed into Asia starting about 50, 40 million years ago. And about half of that climate has actually been shoved under Asia. So the Tibetan Plateau, underneath that, is actually half of what used to be India. This vastly increased rock weathering, because believe me, in most of Earth history, you cannot walk to the stratosphere on Earth. You can fly to Nepal and walk up on top of Everest and be at the bottom of the stratosphere. That's really unusual. That doesn't happen all the time. And the effect is that you hugely raise this chunk of ground, and that vastly increases rock weathering because you're exposing the rocks to all sorts of glacial and weathering processes. And so the rock weathering just went way through the roof. Hasn't been this bad for 400 million years. And that sucked about 80% of the CO2 that used to be in the Cretaceous atmosphere. The atmosphere 50 to 100 million years ago. Sucked 80% of that out of the atmosphere. The way you weather rocks, and again, I can go into excruciating detail, is that basically you make carbonic acid from the CO2. That helps break down the rocks, but it gets trapped in the broken down rocks, sent off and deposited in the ocean. What's happened with losing all this CO2 is you've made the climate vulnerable to small changes in solar energy inputs. Because one of the things that you never realize, especially living in Florida, is that you actually have a modest variation in solar energy input. And it's most pronounced in high latitudes. So these small orbital variations, once you take the CO2 out, because what the CO2 does is it basically homogenizes the atmosphere and transports heat very effectively to the poles. You take that CO2 out, you get really cold polar regions and really cold northern regions. And so these small orbital variations can have big effects. This is the last glacial maximum, 18,000 years ago. You had a mile of ice on top of New York City. You don't believe me? You can go to Central Park and you can see the grooves etched in the bedrock from the glaciers dragging boulders across the Central Park. This particular one in the picture is right by the American Museum of Natural History. So if you're at the American Museum of Natural History, you go through the gate, this particular rock will be on your right as you go through the gate. Don't believe me? Go and look. Yeah, there were a lot of interesting things, like you had continuous sea ice, or you had winter sea ice all the way down to Cape Hatteras. So you can imagine what happens to your condos with continuous winter sea ice. I mean, the polar bears like it, but can you imagine trying to, work it out with polar bears to go have a winter vacation? Anyway, this used to be, the search for the cause of ice ages used to be big science back in the 1910s and 20s. There was abundant evidence that they occurred, because as geologists, you can see lots of glacial features. These are pictures of glacial features. The ones with all the kids, that's what's called a glacial erratic. But why was the climate so different to cause a mile of ice over New York City? Well, distribution of solar energy varies with the Earth's orbit. Right now, you actually get 6% less solar energy when at aphelion, which is when the Earth is farthest from the sun. And although I have a hard time convincing Florida audiences, summers are actually colder than they would otherwise be, because the Earth is farthest from the sun during northern summer. And so we actually celebrate aphelion every 4th of July in America. I always found that very quaint. Anyway, so at our current orbital parameters, we actually have, in the northern hemisphere, we have warmer winters and cooler summers than we could otherwise have. This varies over time. The guy who figured this out was a Serbian mathematics professor named Milankovic. And the whole idea is that these orbital variations, the eccentricity of the orbit, how out of round it is, the tilt, how much the axis is tilted, and where you end up in this during the seasons, so the precession of the seasons, actually has a major effect on climate. And he found that you can change the amount of solar input at high northern latitudes. In this example, it's 65 degrees north. You can vary as much as 25%, and that's more than enough to bring on the glaciers. The basic idea is simple. Warm winters melt the snow that falls in your cold, or warm summers melt the snow that falls in your cold winters. Cold summers allow snow to accumulate. And you have a warmer winter, so warmer air holds more moisture and you get more snow. This is one of the things that amuses me, is that people say, well, it's a lot more snowy now. We can't have global warming. No. That's exactly a symptom of global warming, is snowier winters in the northeast US. I'm sorry, you're just, again, showing your ignorance. So, and our orbital variations have dominated our recent climate. This is the last 150,000 years. So, basically, we had an interglacial back about 120,000 years ago. And then we had a very steady deterioration, basically in response to precession and tilt cycles, until the last glacial maximum, right down there, where you had the mile of ice over New York City. And then it warmed, and that was 18,000 years ago. And then it warmed up very fast to the current climate. These things are always with us. What changed was the loss of CO2. And basically, 4 million years ago, it didn't make any difference because there was enough CO2 that all the orbital effects were above the line that we're at right now. The red line is where we are roughly. What happened is that the climate became vulnerable to periodic ice ages because of the loss of the CO2. And you get these huge swings now, going from relatively mild, but still in an ice age, to extremely cold and extensive ice formation. You also get other things like enhanced monsoons, but we'll talk about that later. So the last million years is long glacial periods, short spurts of warming, all driven by orbital variations. And this is entirely predictable because we know these orbital variations very precisely. Probably the most boring planetary scientists you'll ever find are people that track orbits to 12 decimal places. And we know these things very, very precisely. So what does this mean for us now? If we know this thing very precisely, we should be able to calculate where we're going and where we've been, and people have done that. And the thing is that you had a relative peak about 10,000 years ago that warmed up from the glacial maximum, melted ice, and then the climate started to deteriorate. And we should have dropped back into a mild ice age by now. But we didn't. There's a little lag in effective peak warming because you have to melt ice, and ice takes a long time to melt. But our peak warming was about 8,000 years ago. Since then, solar output has been dropping, but the ice is still retreating. And again, here's the other part of this equation is greenhouse gases. What happened about 8,000 years ago is our ancestors invented agriculture. And, well, they actually started more like 12,000 years ago. But eventually they ran out of already open fields. And so 8,000 years ago, what they started doing was clearing fields with slash and burn agriculture. And taking trees and burning them is a great way to put CO2 into the atmosphere. And we can see this in the historic data, that you had what is the expected trend from Milankovitch, and the actual measurements of carbon dioxide started moving off that trend about 8,000 years ago. How do we know? Well, this is another thing that I learned standing in the freezer, is that Antarctic ice traps gases from when it was formed. And so these bubbles are direct samples of the ancient atmosphere, and we have atmospheric samples going back 800,000 years. So it's not a guess, it's not a model, it's not a prognostication. This is actual data that we know to high precision. And one of the things I got to do, I was cutting up these ice cores. Sometimes they just shatter. So what I'd do is I'd save the shattered pieces, and on Fridays we'd have happy hour in the lab. And this is like 50, 60, 70,000 year, 100,000 year old ice, ice that before we were a species. 200,000 years. So nice clean ice, and these bubbles are under pressure, so you throw it in your scotch and it fizzes. It's really cool. God bless the National Science Foundation. Same thing with methane. 5,000 years ago, our ancestors invented rice cultivation. They domesticated livestock. Great source of methane is rice because rice is a swamp grass. Methane is a swamp gas. And of course, livestock. Anybody that's been on a farm knows that livestock fart. They make methane like crazy. And they also deforest. I mean, goats and sheep are just one of the most potent factors in deforestation. Because any area where goats and sheep are grazing, all the little trees, all the seedlings get eaten. And after 100 or 150 years, there's no more forest. And again, this is not human time, we're talking geologic time. So you ever walk in the South Downs of England, it's beautiful, wide open spaces. But this would be an oak forest, and we would be able to see about 10 feet if it weren't for the sheep. And you can actually see the sheep in this. Yes, these are the actors in deforestation right down there. Anyway, and you say, well, hold it, agriculture is recent, right? No. Agriculture became widespread in ancient times. And really, you had agriculture moving into the far northern regions of England and southern Scandinavia 6,000 years ago. It really began and spread very widely, and of course, same story in China, same story in India. Basically, humans, we have arrived as a force in climate. So forest clearing, rice cultivation, domestication of livestock, basically stop the insulation cycle from cooling the climate by cranking up the greenhouse gases. Now, it's not like prehistoric humans got together and said, wow, we need to deal with climate change. This is inadvertent, it's unplanned, but the effect was to stabilize the climate by the injection of greenhouse gases. And if you actually look at the ice cores, which actually, this is an ice core that I did, you can see that the variation in climate was huge going back 120,000 years. And it really stabilized out with the advent of agriculture. But there's a problem. Milankovitch is moving on where the insulation in high northern latitudes, the amount of sunlight keeps getting smaller and smaller and smaller. And so what you need to do to offset that is get more and more greenhouse gases in. But there's a limit to how many trees you can cut down and how many fields you can cultivate. And by 1600, we'd actually been hitting the limits of what could be done with muscle power in early agriculture. And you were getting climate deterioration like the Little Ice Age. What you needed to do to keep the climate warm is to tap a new reservoir of greenhouse gases. Enter the Industrial Revolution, enter the advent of fossil fuels. And remember, the whole pre-industrial climate, our whole pre-industrial atmosphere was about 2,000 billion tons of CO2. Right now, we're adding about 38 billion tons of CO2 every year. So, in my lifetime, I'm an old guy. In your lifetime, we've actually added a significant percentage of what the original CO2 content was. And it's actually not very hard to see this in the data. Humans actually started affecting things back over here. And you can see that modestly added. And then, of course, here's industrialization. And I actually did Dome C and Law Dome in this set of data. And of course, the result is rising temperatures. People say, well, CO2 is just part of a natural cycle. Well, as I said, we have exact CO2 data back 800,000 years. That's the natural cycle. Does the last 100 years look like it's part of the natural cycle to you? I think not. We actually know the isotopic ratios of the carbon in the CO2. And of course, you can tell, big red herring, or just like a sore thumb, the fossil source carbon sticks out because it turns out that fossil carbon is a lighter isotope than atmospheric carbon. So your isotope ratios change and drop like a stone. What about volcanic sources? People say, well, maybe all this came from volcanoes. All volcanic sources contribute about 0.7 of a gigaton per year. Human output is 50 times higher than all volcanic sources. Well, maybe the temperatures are caused by increased solar activity. Nah. We know solar activity. We track it very carefully. The yellow is solar activity. The red is the temperature. And of course, every year keeps getting hotter. I teach a climate class. Every time I teach it, I get up and say the last 10 years are the hottest years in recorded history. And I've taught that for 10 years. So I keep having to get new slides to show it. And of course, the problem is that 2024 actually broke the line of 1.5 degrees C above pre-industrial temperatures. And you can do a lot of these. Average Arctic sea ice extent, Greenland ice sheet mass loss, average temperatures. With increases of CO2, you'd expect the biggest effect to be in the high northern latitudes. Oh, what a shock. There they are. The National Snow and Ice Data Center had this archive of old black and white pictures taken of glaciers, of lowland glaciers in Alaska. And what they did was they went back in the 2000s and went to the same place and took the picture of the same view. I like this one because you can see the bathtub ring left by the old Muir Glacier right there. Very cool. The other thing I really come away with from looking at this stuff is just how cold and miserable Alaska was back before global warming. So, in many ways you can say, oh man, Peterson, OPEC, Northwestern, God, that looked miserable. Permafrost is retreating north. Climate zones are shifting north. We've moved about half a plant hardiness zone since 1990. Tornado Alley, when I was young, was in Oklahoma City. Now it's in Birmingham. So I was born in 1950. When I first drew breath, CO2 emissions were about 5 gigatons a year. CO2 level was 310 parts per million. Now they're 38 gigatons a year. CO2 level is 428 and change. And so CO2 will probably reach double the pre-industrial level by the end of this century. So something like 560. What's that mean? Well, 560 parts per million CO2 is like the world 10 million years ago. And as I keep saying, this is not rocket science. I actually do rocket science. You can just read the conditions out of the Miocene sediments. And lots of places in Florida have Miocene shorelines, but they're all around here. So you can imagine that the Miocene shoreline is going to be in the spine of Florida, and everything else is underwater. So you'll see disappearing Arctic sea ice. Mountain glaciers go away. You get unstable calving glaciers in Greenland, which is not so bad because Greenland's in a bowl and it's hard to get the ice out rapidly. But your real problem is the West Antarctic ice sheets. And those things can slide downhill really fast. You'll get forests moving north, so the forest line in Canada will go way north, and also in Siberia. You'll get stronger monsoons. So the irony is that during these warmer times, it's actually wetter in the deep deserts, like in the Southwest and in North Africa and Saudi Arabia. And already this year, this last monsoon season was extremely strong in North Africa. It's happening already. And you should expect somewhere around 2 meters of sea level rise this century. And as I say, this will probably happen this century. And my bottom line, because people talk about things like, extinctions and acid oceans and stuff like that. But from a geologist's point of view, the question you have to ask yourself is, do you like sea level where it is? Yes or no? And if you don't care, we're done. I can't convince you that this is a problem. The sad news is that 40% of the continental glaciation that was around during the last glacial maximum never melted. This is what is left over in Greenland and Antarctica. And we could eventually, it will take geologic time, not human time, but eventually have 230 feet of sea level rise. Now, this will be hard on Florida. On the other hand, Pine Bluff, Arkansas becomes a major seaport. Some people gain, some people lose. Sea level's been rising. I was talking about this some years ago in a bar in San Juan Islands in Friday Harbor. And this guy said, well, I don't believe in global warming. I said, well, you don't. It's not what scientists say. You observe global warming. He said, I think you're wrong. So, and then he said, do you want to bet on sea level rise? I said, sure. And we talked about this, and I got him to give me 3-to-1 odds on essentially no sea level rise. And then I made a huge mistake. Because he said, well, how much do you want to bet? I said, well, $25,000, because my children will love you. And the sea level's already risen way more than what we'd bet on. So that spooked him. I'm not sure he believed what I was saying, but he certainly didn't want to bet on it. Anyway, I think we're pretty well locked into about 1 meter of sea level rise. I think that it depends on the physics of glacial decay and calving on the West Antarctic ice sheet, whether we get 2 meters. I'm not very optimistic. I think in 30 or 40 years, this will be kind of the West Antarctic ice sheet calving report will be a big thing. But what does 1 meter look like? Well, 1 meter of sea level rise is the little red areas. This slide shows that they don't have really good elevation data for a lot of South Florida. But this would be very hard on the Keys and be very hard in places like Crystal River, the Mississippi Delta. But Miami Beach is going to have a real problem. And you say, well, why don't you do what they do in Holland and just build seawalls? Well, in Holland, they're not building on porous limestone. You can build all the seawalls you want for Miami Beach, and the stuff will just percolate up through the ground because it's porous. And almost all of Florida is porous. And seawalls are not going to make a damn bit of difference. So what they're doing in Miami Beach right now to deal with this 3.2, this 1 meter rise, is they're raising the level of the streets 3 feet, which the problem, of course, is all the foundations are still at that other level, and I'm sure that that getting mortgages is going to be increasingly difficult in the back bay of Miami Beach. The other thing is if you've got a sidewalk cafe and they raise your street 3 feet, you end up with a sidewalk swimming pool. So anyway, answers. Of course global climate varies. It's been varying constantly over geologic time. Of course human action is warming the planet. If we were just following the Milankovitch cycles, which had been following for the last many million years, we would be seeing glacial advances, but we're not. We have changed the greenhouse gas levels, and that stopped the current Milankovitch cycle in its tracks. What we're doing is geoengineering the atmosphere. And we've been doing that since humans started slash and burn agriculture. It's not like this is exactly what we're happening. And the whole thing about geoengineering something is that you need to take a little bit of responsibility and action and geoengineer the thing the way you want it to turn out. And I personally like sea level where it is. And it's certainly possible to geoengineer the atmosphere to preserve the current sea level. So what can you do? Well, again, this is not soundbite science. It's also not rocket science. You need to put fewer greenhouse gases in the atmosphere. You don't necessarily have to get all your energy or most of your energy from fossil fuels. There are lots of alternatives. And if you ever want to invite me back, and if I haven't been too depressing right now, I can tell you how to do this. Because a lot of the technology that's been developed, particularly by the oil companies, is applicable to getting energy without fossil fuels. And so I will leave you with that. This is a tractable problem, but it is a geoengineering problem that we need to actually take a little initiative and agency to solve. Thank you very much.
So I'm sure we have some questions here for Dan, so I'm ready to throw the box. Here we go. You ready, sir? Can you catch this?
Are we on?
I can hear you.
Okay. The type of geoengineering you're referring to, just a short comment on how that will be done, what elements that will take to do it, how much cost, how much time, and so forth, as opposed to what we're doing now.
Well, the fundamental problem is it takes a while to get the CO2 out of the atmosphere, but it does decay reasonably fast. You're not talking geologic time, you're talking 50, 100-year time frames. So part of this is slowing down the inputs, but recognize that although I like sea level where it is, I don't want a mile of ice on New York City either. So you need to burn some fossil fuels. You need to keep some enhanced level of CO2 in the atmosphere in order to maintain what would be an equitable climate. And the climate that we actually should be shooting for was something that was a CO2 level that we blew through back about 1985. So, in the back.
Oh, okay. Jose, I got you. You got this one first.
And of course, I should say, speaking of agency, this all mostly happened during my lifetime. So I am certainly as responsible as anybody for this. And I apologize to my students at UCF whenever I start this class that, yes, it was my generation that did this. I'm sorry.
So I guess I was curious, if there was a major volcanic activity, something that would maybe potentially affect the atmosphere for a few years, what would you think that might do to the CO2 in the atmosphere?
Well, even the really large volcanoes, like I showed a picture of Pinatubo, which is the largest volcanic eruption for the last 50 or 60 California easily burns more fossil fuels and puts in more CO2 than the largest volcanoes. So the nice thing about volcanoes is they throw dust in the stratosphere, so they actually cool things down for a few years. But the dust falls out pretty fast. You know, the last really big one was Tambora in 1816, and that created the summer without the year without a summer. It also led Mary Shelley to write Frankenstein. So you can get a lot out of volcanic eruptions. Yeah.
Thank you for your lecture, it was excellent. Do most scientists believe that the Paris Accord was a good framework to control global warming?
Well, you're using the word believe again. I don't like it. I don't even believe in gravity. I observe gravity. That said, the Paris Accords and almost all the discussion I hear from political folks is missing the point, which is that we have agency to control the atmospheric chemistry, and that we should aim for controlling the atmospheric chemistry the way that pleases us. Now, that's a really hard sell, other than saying, well, we should just go to net zero. And net zero is an okay first step, but recognize that, again, you don't really want the ice advances. But it'll, of course, take a long time to scrub CO2 out of the atmosphere. And the irony of this is that being a geologist, I go to meetings like American Association of Petroleum Geologists and hang out with these guys because they have like the best exhibits of any meeting I've ever been to. They pass out all sorts of free stuff. Aramco gives you free barista coffee. And so it's a great meeting. And I've given talks there. And they have this side business because they recognize that sooner or later people are going to want to scrub more CO2 out of the atmosphere. And so they're working on side businesses to do that for vast amounts of money, of course. So, that's part of the future also. Another part of the future is a much greener Saudi Arabia and North Africa, ironically. So.
Okay. I got you. Ready? Can you catch?
What is the best thing someone can do as an individual to, I guess, help?
Well, burn less fossil fuel. What I did 6 years ago was I took advantage of a generous federal subsidy and I put solar panels on my house. And I haven't paid for electricity since. Duke Energy pays me a trivial amount, but I'm 2.5 gigawatts or 2.5 megawatts to the good every year from my electrical generation. What I really need to do is buy an electric car. And because a big chunk of fossil use is generating electricity and short distance transportation. Because the average commute is 30 miles. And electric cars have far bigger ranges than that. We just don't have the charging infrastructure that they've developed in a lot of places. And once we get that, and rapid charging in easy places, it makes a whole lot more sense to drive an electric car because they're 3 to 5 times more energy efficient than an internal combustion engine. Internal combustion engines are just nightmares for energy efficiency. It's way more efficient to even burn natural gas and generate the electricity and then put it in your car than it is to put gasoline in your car.
Yeah, something you alluded to earlier. There are technologies being developed to extract CO2 from the atmosphere. Given what's available now, do you see that as something that can, in the next 50 to 100 years, extract enough CO2 to make any difference?
Well, the reasonable cost, no. The problem is that you're talking about billions of tons of CO2, 38 billion tons per year. Can you imagine what a pile of, just converting it to carbon, that would be like 13 billion tons of carbon. Can you imagine what a pile that would look like? It's hard, but there are people that are working on this. And there's a number of technologies. There's a lot of scrubber technologies. In fact, a lot of this was pioneered by the Navy, because your problem in nuclear submarines is that you dive and you don't get to refresh your air supply. And sailors expel CO2 and methane all the time. If you've ever been around sailors, you know. And so they've actually developed decent scrubbing technology, but scrubbing relatively low levels of CO2 and methane out is kind of hard. It's very energy intensive. And so what they do in nuclear submarines is they let the CO2 level rise to 5,000 parts per million. And I once talked to a vice admiral of submarines, and he said, yeah, everybody gets a first 2 or 3 day of the cruise headache from that level of CO2, and everybody is kind of snippy for the first week, and then, you get used to it. And so what they do is they cheat. They allow the level to rise. If you're just going to suck it out of the air, it's very energy intensive, and then you have to put it someplace. One of the ways you can do it is recycle depleted oil and gas formations and pump it underground. So that's another thing that you learn a lot about in the American Association of Petroleum Geologists. You also learn all sorts of obscure places that really want to attract oil investment, because there is a lot of oil in the world. The problem with oil is not scarcity, it's managing abundance. That's why there's an OPEC.
Okay. Here you go.
Thank you. The question of whether to buy an electric vehicle, it's always this discussion about how it costs more energy to create this vehicle, and that we're using the energy to feed it electricity based on fossil fuels. And so is this a cycle that's actually going to improve so it's efficient enough so that we're not putting in as much as we're taking out?
Well, I think the short answer to that is no. That it is way more energy efficient to just drive the car. Remember that you have to have energy for the steel. The batteries require a bunch of relatively rare and socially problematic minerals. The places that you get minerals for these things are places like Indonesia or the Congo, where people are fighting civil wars over access to these minerals. That said, it's way more energy efficient to do this car. I've seen people trying to make the point that it uses more than it saves, and the numbers just don't back it up. I don't have a slide about that to show you, but there is data to say that. My next car is going to be electric, but I want to make sure that they actually solve more of the battery problems before I buy one.
So we might have time for one more question. Does anybody have another question? Okay. Well, we have two. So that's it. I got you two guys, okay? All right.
You just mentioned that we have abundance of oil, but I have read from a few sources that with the current reserve of oil worldwide, and obviously there may be new discoveries, but supposedly from the current reserve, we'll have oil for another 50, 60 years, gas for 60, 70 years, which that's not too far from now. Is that true, or what do you have to say about that?
Oil reserves are not a geologic phenomenon, they're an economic phenomenon. And so it has to do, what ends up being a reserve requires a certain input of exploration and analysis, which the oil companies don't do unless they think they can make some money in a reasonable amount of time so that it doesn't drag down the quarterly report. When I was getting my master's in economics, in natural resource economics, people were saying the exact same time and saying, oh, we'll be out in 50 years. There's a thing called the Hubbard Peak, and we're almost there. And of course, that was 50 years ago. So the short answer is no. Several things change. First, you explore more and you find more stuff. Second, technology changes so that stuff that was uneconomic becomes economic. In the 80s, the big issue was how do you extract oil from shale? And literally, they were open pit mining shale and grinding it up. And now they frack it, and it works really well. And some of this fracking technology can be actually used to develop geothermal power and clean energy. So there's lots and lots of oil. There is so much oil, it's jaw-dropping. And we try to avoid thinking about things like the whole Siberian continent has not been touched at all for shale oil. And there's probably more shale oil there than there is in all the United States, which is the richest source of shale oil. Anyway, so no, we're not going to run out. And 100 years from now, people will be saying the same thing. Whoa, we're going to run out in 50 years. It's one of the few constants in the economics business that people do this.
Back in geologic time, I think you said CO2 was like 1,700 parts per million.
Yes.
What was the rest of the Earth like then?
Hot. Well, the thing is that there's a limit to how hot you can get in the tropics. Because what happens when it gets hot in Florida is that you get a sea breeze flow, and in the afternoon you get towering thunderstorms that cool you off. So where you mostly, when you have lots of CO2, places like Florida are about the same temperature. What you do is you're transporting heat to the poles far more effectively. So essentially you have temperate, either cool temperate or warm temperate climates in polar zones. So you don't, right now we have a polar climate zone and a tundra climate zone and a taiga, boreal forest climate zone. All of those disappear because it would be just too warm. And basically you get temperate, you either get tropics or temperate. And you see that all the time. And it's easy to see in the geologic record because each one of these climate zones produce a distinct sedimentary package. So it doesn't take a lot of imagination, which that's what I like. I just read the rocks.
Yeah, thank you, Dr. Britt. It was wonderful. Appreciate you.